Morning, everybody. Can everybody hear me okay? Yeah, great. Cool. So I'm going to be starting us off today talking a little bit about using ICESat-2 to measure snow depth. So kind of putting together some learning objectives for this tutorial. I'm going to be showing an example of working with slide rule to extract data and then do some pre-processing. I'm going to also be showing how to use projections and interpolation to compare ICESat-2 track data with gridded raster products, and then also trying to develop a general understanding of how to measure snow depth with LiDAR, and learn about opportunities and challenges when using ICESat-2 along track products. So hopefully, even if you're not super interested in snow specifically, there's still some things you can take from this and that will hopefully be useful in your projects. Okay, going into a little bit of background, this image rendered enormously, so I don't know that I can get all of it on the screen at the same time. But I wanted to start with a little bit of background about how do we measure snow depth with LiDAR. LiDAR systems in general have been used to make very high resolution snow depth maps over large spatial areas. It's a very valuable tool. The general methodology is that you have a snow-free digital elevation map, and then you have a snow-on map. And by differencing the two, you can get a snow depth map. You can see this is an example from Deems et al. Showing that methodology. And then you can see an example snowpack that you could derive using this method. So the question arises, ICESat-2 is LiDAR. Can we do this same method with ICESat-2? Yes, we can. There's definitely some different quirks with the data that you have to learn to work with. But by differencing snow-covered ICESat-2 tracks from snow-free digital elevation maps, we can calculate these snow depth transects. Like I mentioned, this is a little different than other snow depth methods since we're working with a transect instead of a grid of data. Also, you can run into challenges where, since ICESat-2 does not repeat particularly often in the mid-latitudes, you're not going to be comparing ICESat-2 to ICESat-2. You're going to want a separate data set for your snow-free reference surface. And we're going to show an example of that in this tutorial. So this is a map from one of my study sites, and you can see the digital elevation model and then the ICESat-2 tracks on top of it. So you can get a little bit of a sense of what we're working with. All right, so what do we need if we're going to calculate snow depth from ICESat-2? We want a region of interest, we want some ICESat-2 data, and we need our snow-free reference DEM. And then what are some of the things we have to think about as we're working with this data? First, we want to think about geolocation. It's really important to have our different data sets lined up properly, since small offsets can have, can result in errors in our snow depth estimation. This is an example from a Newth and Cobb paper showing how in a sloped environment, a small offset is going to create these systematic biases in the data and how that's related to aspect as you go around. So we're not going to talk too much about co-registration in this tutorial itself because that can take a while, but wanted to highlight that this is something that you want to consider. Additionally, vegetation can introduce a positive bias into data if vegetation is incorrectly categorized as ground returns, especially if you're looking at snow in the forest, which is the huge advantage of LiDAR, is that it's able to see that ground surface under vegetation. But we do need to think about those vegetation effects. And additionally, there are slope effects. So in addition to the geolocation issues and how slope can exacerbate those, slope also has been seen to introduce a negative bias into ground or surface estimations. When slopes get up, like above 30 degrees, it really starts to affect things. Okay, now that we've done some background, going to start working through our example. So we're going to start by reading in our Python libraries. If you want to follow along, that's great. You're going to get an error popping up, though it hasn't this time for me. But that's fine, you can ignore that. And we'll start by collecting our ICESat-2 data. So we're going to use slide rule, which we saw yesterday, and we're going to be collecting ATL06 data. And then later we'll read in some gridded raster data for comparison. This is not going to be ATL06 as you would download from NSIDC. This is going to be a modified ATL06 where we're including some vegetation filtering from ATL08. And then for this example, we're going to be looking at data over the Arctic coastal plain of Alaska, which we chose because it's relatively flat. There's not a lot of vegetation. So it's a pretty good site to use this method. All right, so we're going to initialize slide rule. And then we need to define our region of interest, so slide rule knows where to look. There are two different ways we're showing here. You can set up a bounding box just by giving coordinates, or you can read in a GeoJSON. We've provided the code for both. And then if you wanted to read in the GeoJSON, we also have that file in here, so that'll load. Next, we want to build our slide rule request. So we're going to build this request by defining our parameters. Since we want the ATL06 product, we're going to use the ICESat-2 ATL06P function. I've included a link to the documentation here. Here. And then I've also included a reference to some of the parameters you can use. This isn't all of them. There's a few more that you can see on the slide rule user's guide. We also won't be using all of these parameters in this tutorial, but wanted to have this reference for people. If we all run this next cell together, it might take a really long time. So if you are running it and it doesn't seem to be going anywhere, feel free to terminate it. We have the data available and we'll read it in later if you want to follow along with the rest of the tutorial and slide rule doesn't work in this moment. So yeah, now that we have our parameters, we're defining them in this section here. We're setting our polygon to the region we defined above. And then we're setting that we're looking at the land, high surface or high confidence surface photons. Here we're introducing our ATL08 ground classification and a few more parameters. All right. And then here is where we're reading in our parameters and running slide rule. So we'll just, or I ran this earlier just to make sure I didn't have any issues, but I'll give everyone some time if they want to try running this. And this is the data file that is going to get spit out. Okay. Yes. ATS. I don't remember off the top of my head. Thank you.
It basically filters out the segment if there's not a long enough distance between photons. So you don't want to have a segment that only have like photons in one place where things are exposed to that. So you want to be able to filter based on how far apart.
Thank you. If we drop down here, whoops, we can go over what are all the parameters we defined. So we defined our region above. With SRT, we defined that only land photons are going to be considered. CNF was our only high confidence photons. ATL08 class, only ground photons as identified by the ATL08 algorithm. ATS, maximum along track spread, setting that to 5 meters. The length, so that's setting the length of each segment to 20 meters. The resolution, the along track resolution was set to be 10 meters. So because we have a 20-meter length, there's going to be a 10-meter overlap between each successive data point. And then Maxi is setting that the refinement algorithm is going to iterate 5 times per segment at maximum. Okay. All right, now that we've pulled our data, we want to subset it. If you're pulling a ton of data, it can take quite a bit of time. We have a rather large region of interest, and we've attained the ICESat-2 tracks, like all ICESat-2 tracks since launch. So we can plot those really quick. This might take a second. Thank you. There we go. So you can see we pulled rather a lot of data. Oh, I think I used the bounding box and not the shapefile, which is why it's gone beyond the borders of the shapefile. So that is one of the nice things about the shapefile, is that you can pull from different shapes if you want to. But yeah, so we can see we have quite a bit of data here. And maybe we don't want to look into all that data. So our LiDAR DTM is only available for March 2022. So we're going to pull just our March 2022 data. So we're going to subset this data to include only one ICESat-2 track, the RGT 1097 in March 2022. Oh.
How do you know what track number? How do you know what track number goes with what date?
We're looking up here. We have time, and then our RGT value is right here. So you can, you can see what is going to align with the date you're looking at. Okay. So, yep, here we're setting that we're subsetting to that particular RGT, and then we're also subsetting the time. Okay. And we can see that output here. And we can see that we have just the reference ground track that we want, and then all of our times, at least in this the section it's showing us, but we can assume that this is true for the whole data set, is March 2022. Okay, so this next section is if slide rule took too long to run, we also provide the data. So you can run this code, and it's going to produce the exact same thing that we just made using slide rule. It's just something we prepared ahead of time. Okay, and now I'm going to hand it off to talk about the rasters.
Okay, can everyone hear me okay? Just to make sure. Sweet. All right, so thank you, Karina, for starting us off with getting our ICESat-2 data ready. So now we are going to shift gears and take a look at some of the DEM data, and most importantly, try to co-register that with our ICESat-2 data. So the data set that we're going to be working with is a raster that was generated from the University of Alaska Fairbanks. It was generated from a LiDAR that has 0.5 meter resolution and was flown at a near infrared wavelength. So if anyone is familiar with the Airborne Snow Observatory, this is essentially the same data set, but flown out of Alaska Fairbanks as opposed to the Western United States. So in order to read in this data, we are going to use the package Rio X-ray because that's, at least from my experience, that's generally the best way to read in LiDAR rasters because it has this built-in function known as Open Rasterio, which allows us to read in the rasters fairly quickly and efficiently. So this first cell right here, it defines, it shows us where the path is to the LiDAR data is. I provided it within a shared public folder just for the sake of this tutorial. And although it's normally at 0.5 meter resolution, I went ahead and coarsened it to 3 meters because otherwise co-registering it with the ICESat-2 data would take forever. And I don't want to just keep y'all hanging here. So I'm going to run this cell. And even though it doesn't bring up anything, we now have 2 LiDAR rasters loaded. One of them is a snow off raster, and one of them is a snow, and is essentially a snow depth product. And we need both of these because the snow off data we need in order to estimate the ICESat-2 snow depths. And then we need the snow depth product essentially just to have that validation data set available for us. So it's not immediately obvious, but the ICESat-2 data and the UAF LiDAR are not in the same coordinate reference system. ICESat-2 uses latitude-longitude coordinates. It uses, in other words, WGS 84, whereas the LiDAR is in a completely different reference system. So that means we need to try and reproject one of them in order to get them on the same reference frame. And so that's what this next cell is here for. Essentially what we are doing is taking the ICESat-2 data and we are reprojecting it from those lat-long coordinates to easting northern coordinates. And thankfully in GeoPandas, it's pretty easy to do that. As long as you have defined a coordinate reference system already, you can use this function 2_CRS to change to another one. So if I run this, and we go over to the geometry tab, you can see that we no longer have lat-longs, but we instead have easting northern coordinates. And it was very quick and easy to do here. All right, so now that we are in the same coordinate reference frame, we are going to do the co-registration. I'm not going to go through this entire cell just because this is a very long and ugly function. It's honestly something that I would write as like a helper function and then put it under the hood. But there are just like a couple of things that are worth mentioning here. First of all, we are using what is known as a spline interpolant to match the ICESat-2 and LiDAR data. And then just in terms of the code structure, I just wanted to note that even though that this is a pretty big, ugly function, that just also means it's all the more important to make sure that you try and comment your code as you're going through it, just to make sure that if anybody else just so happens to go through it, that it's generally more understandable to them. One of the ways that you can do that is generating what is known as doc strings, which is this area up here in red. If you're using the Spider graphic user interface, you're able to generate doc strings like this pretty easily, and you're able to basically just create a summary of the various inputs that your function has and the expected returns as well. So just for the sake of time, I'm going to go ahead and just run this cell to define the function. And then this next cell right underneath it takes that function and will co-register the ICESat-2 and the LiDAR data. And I should note that it's co-registering with both the snow off DEM and the snow depth product as well. Just because both of those rasters are of different sizes, and just to keep it simple, it's going to co-register with both separately. So kind of like the slide rule cell that we ran, it can sometimes take a little long just because we have a fair bit of data there. But in this case, it didn't go for too long. So here, this is basically the same data frame that we started off with, but we have a couple of extra things here. So to start off, we still have the ICESat-2 data here, but most importantly, we also have the LiDAR, like the LiDAR snow off elevations and the LiDAR snow depths that are co-registered with the ICESat-2 data. And we were able to do that pretty quickly over this region. We also have our easting northern coordinates. We have the beam. We have a couple of other useful variables that could be highly handy when you're doing this kind of analysis. So now that we have this data frame, it's actually very simple to estimate snow depth out of this. And in order to do that, we're just going to do a very simple operation with pandas. One of the nice things about pandas is that you can very easily perform operations between different columns within your data frame. And so in this case, in order to derive the snow depth, just based on those differencing principles that Karina introduced to us, where the snow depth is essentially going to be the difference between our ICESat-2 height and the LiDAR height. And we're doing this because the ICESat-2 data was acquired when there was snow on the ground, whereas the LiDAR data was not. So we're essentially taking the difference between those two data sets to infer the depth of the snow. And then in addition to that, we're also just going to get a residual just to see what the differences are between the ICESat-2 snow depths and the LiDAR snow depths. And so that was pretty fast to run. And so now we are going to essentially do what we did with the original slide rule data and just give it a quick map. And here we go. So this is just a very basic map of some snow depth estimates over the northern coast of Alaska. It's a very thin strip of data, but through this, we can see like the approximate snow depths that we approximated with ICESat-2. That's pretty nice, but it would also be nice to try and validate this with the LiDAR data. So that's what this next cell is for. It's basically plotting the ICESat-2 snow depths for 3 of the beams relative to the UAF data. And so if I run this, we get something that looks like this. Overall, we have a blank plot here because this beam did not go over our region of interest. It was probably out here somewhere, and so it did not get co-registered. Whereas for the other two, generally the agreement is pretty good. You can see that that the snow depths seem to line up with each other pretty well, especially with GT2L right here. 3L, it's generally okay, but then we have this weird thing going on here at the very end of the track. And that's something that you would probably want to try and figure out with some additional analysis, like why that situation is happening. And then just for fun, we're going to look at a scatter plot just to see how it looks. And overall, the scatter plot of the snow depths look pretty good. That weirdness in GT3L kind of ruins the scatter plot, but otherwise it looks pretty good. All right, so we derived some snow depths and we did some comparisons and they overall look pretty good. So as a last step, I'm just going to use some fancier plotting tools to plot the snow depths again. This is using a tool known as GeoViews. It's kind of based off of the HoloViews package that Andy used yesterday to plot some ICESat-2 data. But the main difference is that whereas that is able to make interactive line plots and scatter plots, this is able to do the same thing, but over various tile sets or maps. So it requires a bit of a learning curve and it's kind of complex. But once you kind of get the gist of it, and wait a little while, you can get some pretty nice looking plots of your region of interest. So just from running that cell, I was able to create this map using ESRI imagery over the Alaska coastal plain. And it has the ICESat-2 tracks and they're colored based on the differences in snow depth between ICESat-2 and the LiDAR. Something else that's kind of nifty about this plot that I generated is that if I, for instance, zoom in to, well, the zoom in tool is a little weird, but if you zoom into this region, for instance, and if I hover over it, I can add like a little tooltip that allows you to see like specific parameters over the region. So if I go back up to the cell up here, I specified this using what is known as hover tool. And using this hover tool, you can specify what specifically you want that hover tool to show you. So in this case, we are looking at both the ICESat-2 snow depths and the LiDAR snow depths. But you can also add things like latitude, longitude, or whatever else data is within your geodata frame. Some other things that you can do with plots like this is, so I have this white polygon here just to show where the LiDAR data covered, but we might want to see like what the underlying surface looks like. And so to do that, what I would do is go to this line right here, map figure, and I would remove this LiDAR box poly because LiDAR box poly is what I use to add the LiDAR box to the map. So if I run this without LiDAR box poly, we get the exact same plot, but without the box in the way. And so once again, we can zoom in and get like a vague idea of what the underlying surface looks like. So yeah, there's a lot of potential functionality that you can use with GeoViews. Again, it is a bit of a learning curve to pick up, but if it is something that you're interested in, then I would encourage you to try it out just because you can make some pretty nice figures out of it. And I don't show it here, but one of the other nice things you can do with these plots is that you can save them as HTMLs. And then once you do that, you can bring them up at a later date. And it basically creates an image, where you can do all this interactivity without having to run the script again. It's pretty handy. So yeah, that pretty much covers most of what we wanted to go over in terms of snow depths. So yeah, at this point, thank you, and we're willing to take any questions now.
Yeah, thanks. Very helpful. That's definitely a capability that I will need in my own work. So the thing I'm wondering is you showed us how to get one data set from one map projection into another map projection, but that only takes care of the horizontal. And I think since we're all looking at ICESat-2 and elevations, we need to be, I think, mindful of reference datum. And I think I had this conversation with NSIDC years ago, said if you compare 25 years of LiDAR data, you can't ignore the reference datum because it changes in the several centimeters level, and so it matters. So how can you do this in Python? So make sure that you're not only horizontally transferring your DEM, but you're also tied to the same reference frame that the other data set has.
Yeah, and by datum, I'm assuming you mean like vertical corrections, essentially.
Yeah, so I mean, it's like everyone says, I use the WGS84, but that's meaningless because you need to tie the WGS84 to an ITRF reference frame, and that changes over time. As I said, I think the biggest change was probably from 2000 to 2005, and that's like 5 centimeters or more, depending on where you are on the planet.
Yeah, and that's a great question. So, and it's honestly a question that still keeps me up at night sometimes, just because I think one of the tricky parts about doing that datum correction is that, at least as far as I'm aware, there's not like a reliable way to do that in Python. It's more like you have to basically plot the ICESat-2 data with the DEM and then see like what the relative differences are. Like do like a snow off comparison between the two and then calibrate from there. That's at least how I've been doing it, because a really tricky part is that, like you said, it seemingly changes everywhere you look. And part of that is because of like different availabilities in terms of DEMs, the different vertical datums, and also just uncertainties with geolocation. So at least from my experience, it is a bit of like a trial and error thing to try and parse out those errors. If there's other folks who have ideas on how to deal with that, I would love to hear them, honestly.
I think if I'm not mistaken, but Proch, the latest version of Proch 4 has the capability to shift between references. So if you can talk to Proch 4 from within Python, there's probably a solution for that.
So how many people have dealt with this problem? If you haven't, you will. It's annoying. Like this georeferencing and dealing with 3D coordinate reference systems it's just one of those things that I wish would go away, but it doesn't go away, and it's time dependent because the plates are constantly moving. A lot of the LiDAR data we have, especially in the United States, is tied to the North American plate. So it's actually moving with the North American plate, whereas ICESat-2 is using the kind of global reference frame. The short answer, we think we've cracked this, okay, and we have some sample code. Scott Henderson and Hannah and JP and a few of us, we've spent a lot of time working on this. So if you're having this problem, come talk to us. Yeah, I could say more, but we can talk more about this later if you want. Yeah.
Could I request like a breakout little session about the method that you do that with? I feel like that could be useful, not just for me, but maybe for other people.
Thanks for that. We will consider that for this afternoon, like we did yesterday with GitHub. Yeah.
Thanks. I'll just note, NSIDC has actually been tackling this problem with certainly with IceBridge, ICESat, and ICESat-2. So we have a tool called IceFlow that allows you to harmonize those data from those 3 data sets to solve this problem. Of course, it's not going to solve problems with other DEMs, but there is that tool out there if you need to use it. It's called IceFlow.
Just add one more quick piece and then a question for Zach. So the 3D transformation you can do with GeoPandas if you pass in a geodetic CRS that has X, Y, Z and defines like ITRF, and your DEM that you're going to also has a 3D geodetic CRS defined, then it'll happen behind the scenes for you. So that's kind of a short answer to that question, but that requires the DEM as well that you're using to have that information. So I think given if the DEM is 2D, this is the best you can do, what's shown in this tutorial. And maybe if there's a ton of snow, it's okay. It's when you're getting down to those like millimeter and centimeter level differences that this is, I think the 3D aspect is especially important. So Zach, it was a really good presentation. I'm wondering about the difference in that one track, and if you have any insights into what's going on there, because it's surprisingly steady as far as the residual goes.
Yeah, that's something that I've been trying to figure out in my own research, honestly. My best guess at the moment is that it would likely be a co-registration error, just because there's a pretty clear difference in just like, if I go back up to the plot, yeah, so if we go back to the plot, the ICESat-2 data has like this clear decrease, whereas the UAF LiDAR does not. So my best guess is that there might be like a slope or something there that would be causing some uncertainty. But yeah, that's mostly just speculation at this point, honestly. Oh, yeah, that's a good question. I think these are pretty close. Let me double check really quick. Sorry.
Can you just restate the question for the audio, because we won't hear it later?
Oh, sorry. How do I do that?
I can just ask. I was
Oh.
just asking what the temporal offset in the LiDAR and ICESat-2 data was, if there could have been a land surface change.
Right. Yeah. So at the very least, it was like within a month. So I'm not super savvy on the Arctic coastal plain, but my best assumption is that drastic changes probably wouldn't happen over that amount of time, unless some other team could tell, unless the DZDT team could tell me otherwise. Or Joe.
To add to the speculation, I think up there within a month, you can definitely have a lot of wind drifts. And also, I think when going back to ICESat-2 and the 40 or 20-meter segments, you have this really like rolling slope tundra things. So I don't know how much offset you have there, but my guess would be there's definitely a land surface kind of change in terms of either wind drift or even like not registering properly to those changes where the LiDAR and 1.5 meters, they can definitely resolve all those little features.
Gotcha.